Hi, and welcome to this lab session on variational algorithms in Qiskit. So in today's lab session, I'm just going to walk you through this Jupyter Notebook file, talk about the code, and talk about the exercises that you can solve. Um, and yeah, pretty much what you're going to learn is, first of all, how to build variational quantum circuits or parameterized quantum circuits in Qiskit. Then how to build quadratic programs and optimization problems in Qiskit, and how to solve these problems using Qiskit's native QAOA implementation. You will also learn how to build your own QAOA variational form, and if you want, you can extend this to run your own optimization procedure. And with this, we can basically jump right in. When you open the Jupyter Notebook, you should see what I'm seeing right now. And the first cell you can execute in order to install all the necessary requirements into your Python environment. And so for me, these requirements are already satisfied. And you can see that the output will clear once this whole installation process is done. So it might take a while for you if it has to download some Python modules, but eventually it should look like this again. And then we can start with the actual Jupyter Notebook. Okay, so there are some imports at the beginning. I'm not going to go into too much detail here, but we'll need them throughout the code in the notebook itself. Okay, the first section of this notebook just serves as an introduction to the topic of variational quantum algorithms. And if you followed my previous talk on the introduction to QAOA, it is mainly a summary of things that I talked about in that lecture. And so feel free to maybe skim this part, or if there are any questions you had about the previous lecture, maybe you can resolve them by looking at this text. Or if you've missed the lecture or weren't able to see it, you can use this sort of as an introductory text to get into the topic. And so, yeah, you can see here basically just some summary about the variational method, variational quantum eigensolvers, and so on. Basically everything you've learned about in the previous lecture. Okay, but we can start right away with the next section, which is about parameterized quantum circuits in Qiskit. In this section, you're going to learn how to, first of all, construct parameterized circuits in Qiskit, and then assign values to circuit parameters. And so by the end of the section, you should be able to build your own custom variational form in Qiskit. Okay, so let's begin by constructing a parameterized quantum circuit. In general, creating a quantum circuit with parameters isn't much different from creating a standard quantum circuit. So what we're going to need is we have to import these two classes, parameter and parameter vector, from qiskit.circuit. And these are the parameters that we're going to initialize. When we initialize a parameter, we basically just call the parameter the initializer of the parameter object, and we just give it a simple string identifier, which is the name for our parameter. And this is also the name that it's going to have in all circuit visualizations. We can then construct our quantum circuit, and we can pass these parameters as arguments to the gates that we're using within our circuit. So if we take this circuit as an example, we apply here, first of all, a rotational y gate, and we pass as the rotation angle our first parameter, parameter 0, and then here we're passing to a rotational x gate, the parameter 1. And then if we draw this circuit, we see the picture down here, where basically we have a quantum circuit consisting of two gates parameterized by two parameters. Now we can also use the same parameter multiple times within the same circuit. So we can build the same circuit as above, just using the same parameter twice. And basically we just pass the same parameter object to both the Ry gate and the Rx gate. And you can see that in the corresponding circuit, we only have one parameter called theta in this case. Okay, if we want to create a variational form with a lot of parameters, we can use the parameter vector class in Qiskit, and this allows us to create multiple parameters at once. As an example, we can consider the following real amplitudes variational form. This is a variational form which you can also find in the Qiskit circuit library. And so this form consists of alternating layers of rotational Y gates and then entangling layers where we apply CNOT gates between the different qubits. And so let's see how we would actually build this in Qiskit. At the very beginning, we just set the number of layers in qubits that we want. Then we can use the parameter vector class to initialize a list of parameters, all called theta. And so when we use the initializer for parameter vector, we have to pass a string identifier, just as when we initialize single parameters. And then we also have to specify an integer value, which specifies the length of the parameter vector, so the number of parameters that we want. And so then, just as before, we can construct a circuit. Here we're going over a for loop for all the different layers, and we first of all apply the parameterized Ry rotations, where we can now access a particular parameter of the parameter vector by passing in an integer in these square brackets. And then afterwards, for each layer, we append the entangling CNOT gates, and at the very end, we append one additional layer of parameterized Ry rotations. And then again, if we execute this code, we get the variation form that you can see here. And as you can see, the parameters of the parameter vector appear in our circuit visualization with the name that we gave to them. And then in square brackets, we get the corresponding number. So this would be the 0th entry of the parameter vector, the first entry, and so on. But these are all just normal parameters, and they work just as the single parameters that we've used before. Okay, if you want a list, or rather a parameter view is what it's called, but it can be converted to a list of the parameters that are part of a quantum circuit, you just call circuit.parameters. And it will, as you can see, give you a list of the different parameters in the circuit. In this case, theta 0 to theta 8. Okay, then if we have a parameterized quantum circuit, before executing it on a quantum backend, we need to assign values to these parameters. We cannot simulate or execute parameterized quantum circuits that don't have assigned values at the moment on quantum backends or simulators. And so to do so, we can use these two methods of the object quantum circuit. We have the method assign parameters and the method bind parameters. The method bind parameters we can only use to assign numeric values to the parameters in the circuit, and this method always yields a new circuit. With assign parameters, we can first of all not only bind numeric values to parameters, but we can also substitute parameters by other parameter expressions. And then additionally, we can specify with this argument in place that no new circuit should be created, but instead the substitution should take place in the original circuit object. And so let's see how we would actually do this in practice. When we use these method assign parameters or bind parameters, we specify the parameters either as a list of parameters or a list of values, in which case the parameters will be, or the values will be bound to parameters in exactly the same order as parameters were added to the circuit before. Or we can provide a parameter dictionary. And in this parameter dictionary, the keys should correspond to the parameter objects that we want to bind to. So recall that the variable parameters here referred to our parameter vector that we created up here. And so this dictionary contains as keys the different parameters that are included in this parameter vector, and as values, the values that we want to bind to them. We can also print this parameter dictionary, and it looks something like this. We have the parameter elements here, and then here the values that we would like to bind to them. And then we can use the method assign parameters to assign these parameters to our circuit. And we get a new circuit where the values are actually fixed to some, where the angles are actually fixed to some numeric value. Okay, this version of the quantum circuit can now be executed on a quantum device. And maybe just as a reminder on how to do that, let's try doing this with with Air's state vector simulator. We first of all have to get the backend. This is this line. And then we just execute this method run on our simulator with the argument of the circuit. And the result of this will be the result object from running our quantum circuit, and we can get the state vector, in this case because we're doing a state vector simulation, by calling getStateVector on this new result object. And then plotting this state vector, we can see that it worked. Now, if we take the original circuit, this was the version of the circuit that didn't have any parameters assigned yet, and we try to run this on the simulator, we see that we run into an error. And so this is because this circuit contains parameters that haven't been assigned values yet. Okay, so this is pretty much it for parameterized circuits. And with this, you should already be able to, first of all, create your own variational forms. And second of all, assign parameters and actually execute these circuits on simulators or devices. Okay, so in this next section, we will briefly review the MaxCut problem that I've already introduced in the last lecture. And we will also learn how to construct quadratic programs in Qiskit and construct optimization problems in Qiskit itself. So first of all, as a quick review for the MaxCut problem, remember that in the setting of MaxCut, we have as input a weighted graph G or unweighted. And as output, we would like to produce the maximal cut of this graph. And also remember that a cut corresponds to a partition of the vertices into two different subsets. And the value of the cut is the cumulative weight of the edges connecting vertices from different sets. And so here's a short recap or summary of the MaxCut problem. You can read through again if you're working through this notebook yourself. But what we're trying to do now is let us just take a look at one specific MaxCut instance and sort of explore this instance a little bit. And to do so, we can use the NetworkX module. We imported this under the name NX here. And first of all, we're going to create a sample graph. So this is what we do here. We just create the graph and add nodes and edges from this edge list. And then we have this MaxCut widget, which basically displays a graph. And you can use this to kind of play around and choose different cuts and see how the cut weight changes as you choose different partitions into two different subsets. This is also where the first exercise takes place. And basically, you're trying to find the maximum cut for this example defined above. And you can use the function that is defined below for this, but you will have to provide some of the code yourself. So what this function is supposed to do when it's finished, it's supposed to print a histogram of all the different bit strings and corresponding cut values. And so it's going to look something like this once you finish. But right now, if I execute this code, it will just show an empty histogram. And so the basics of this function are already given, but you're going to have to insert the code here to compute the cut value for a specific bit string. And you can use the explanations above to do so. Okay, this brings us to the next topic, the topic of quadratic programs. And in this section, we're going to learn how to actually formulate or create quadratic programs in Qiskit. And then later on, we will see how to solve these with QAOA. So just as a quick reminder, a quadratic program is a quadratically constrained is an optimization problem with a quadratic objective function and linear and quadratic constraints. And so let's see how we can create an object that corresponds to a quadratic program in Qiskit. So the quadratic program class in Qiskit is located in the Qiskit optimization module, which is part of the new applications module that were rolled out by Qiskit only a few months back. And so to generate a new quadratic program or a new model, we simply call the initializer quadratic program and we give it the problem name. I call this one just sample problem. Now, if you want to add optimization variables to this problem, we can use the respective methods called binary var, integer var, and continuous var. And actually, let me real quickly copy this line down here. So by calling this function export as LP string, we convert our quadratic program to a string in a readable format. And so by printing this, we can see sort of how our quadratic program changes as we go along with this code. So at the beginning, we have this quadratic program, which is completely empty. We don't have any optimization function, and we don't have any constraints or bounds. Now, again, as I said before, we can start adding variables by calling these methods binary var, integer var, and continuous var. And so if we do that, we see that we have now added optimization variables to our problem called x0, x1, and x2. In particular, if we add integer or continuous variables, we can also provide lower and upper bounds for these variables by setting the argument's lower bound and upper bound. Okay, then to actually add an objective to the quadratic program, we call the methods minimize or maximize, depending on whether we want to look at a minimization problem or if we're dealing with a maximization problem. Within these methods, we provide the quadratic term of the quadratic program as either a list, a matrix, or a dictionary under the argument name quadratic. Same for the linear part under the argument name linear. And then we can also add a constant offset under the argument name constant. And so right here as an example, I've created a matrix consisting of these values, 0, 1, 2, 3, 4, 5, 0, 1, 2, a linear part that consists of the values 10, 20, and 3. And then by plugging these into the quadratic program.minimize function, we can set the objective function of our quadratic program. Right, so there's a bit more things you can do with quadratic programs, and if you want to learn more about it, you can follow the link here, which will lead you to a tutorial that goes into a bit more depth about how to add different constraints, how to remove constraints again, how to convert quadratic programs to a dogplex model, and so on and so forth. But for us, we're going to move on to the next section, which is about max-cut problems formulated as quadratic programs. So again, this is kind of a recap of the theory behind it, where basically we derive how the corresponding QUBO for a max-cut problem looks like. And so this is the topic of exercise 3, where you're going to complete a function that is taking as input a max-cut graph and is supposed to produce the corresponding quadratic program of the max-cut problem instance. And so if we take a look at this function, most of the code is already in there. Here we are getting the weight matrix of the graph. We are then creating the corresponding QUBO matrix and the QUBO vector. And we are using the formulas defined above that you can see here in order to initialize this matrix and this vector. And so the only thing missing here is your code where you need to actually build the quadratic program. And so you're going to have to use the methods that we went through above in order to create the quadratic program and return it. Right, and so this is all explained in the exercise description as well. If you manage to do so, what you should get is something that looks like this. So this is our method applied to the graph that we have defined above. And so for this one sample graph instance, we get the following quadratic program. Okay, this concludes the section on quadratic programs. So now you should be able to define your own quadratic programs and basically put your own optimization problems into a Qiskit object. Then in the last section about QAOA, we will actually learn how to implement our own version of the QAOA variational form. And we will use Qiskit's QAOA to solve the max-cut problem that we've defined in the previous sections. Okay, again, as a little reminder, this is a section about the QAOA variational form. So just to remind you real quick, the QAOA consists of, first of all, a preparation of the equal superposition state, and then p repetitions of alternating cost and mixer layers that are parameterized by these parameters gamma and beta. And so this is explained in more detail down here, where I also go into detail about how the mixer Hamiltonian and the cost Hamiltonian look like. And we sort of derive again how the cost Hamiltonian, cost Hamiltonian looks like, but also how the exponentiated version of the cost and mixer Hamiltonians looks like. And so these are exactly the layers that we want to introduce in our QAOA circuit. And so as an example, we can take a look at the corresponding QAOA circuit for the graph instance that we've defined above. And so to do so, we just import the QAOA ansatz that is already present in Qiskit, which is located in the circuit library of Qiskit under nlocal. And then we have to, first of all, convert our quadratic program to a Hamiltonian operator. And we do so by calling this method toIcing, which will turn this into an Ising operator and basically give us this operator H up here. We can then use the initializer of the QAOA ansatz with a depth of p equal to 1 and a cost operator that corresponds to our Hamiltonian operator. And this already gives us our QAOA circuit. The only thing I've also done here is to replace the parameters in the circuit, so they are named as the parameters up here are as well. So I've just changed the names to gamma and beta in this circuit. And so we get the final version of the QAOA circuit, which consists of, first of all, the Hadamard layer that we talked about before, then the cost layer consisting of RZZ gates, which are decomposed here into CNOT gates and single RZ rotational gates. And then at the very end, you can see there is an RX rotation applied to each qubit here. And this corresponds to the mixer layer of the QAOA. Now in exercise 4, what you are going to do is you're going to build your own QAOA variational form. So you've already learned in the previous sections how to build variational forms or parameterized quantum circuits, and you're going to have to put this to use here. Again, the general structure of this function is already given, so let's take a look. The function takes as input, first of all, the quadratic program and the depth parameter p, and it's supposed to return the parameterized quantum circuit. Now, we begin by, first of all, converting the QUBO objective, the quadratic and linear QUBO objective to a matrix and a, oops, this is a typo, I should say QUBO, a matrix and a vector here. Then in the following, we first of all prepare the empty quantum circuit with the corresponding size, and then we already applied the initial layer of Hadamard gates to all qubits. We then create the parameters that we are going to use in the circuit, and this is where your code is supposed to come in. So we've already created this outer loop to create each individual QAOA layer, but you are going to have to insert the code where we actually apply the cost and mixer layers here. Right, and at the end, we measure the output and we return the corresponding quantum circuit. Okay, this brings us to the next section where you're going to learn how to use the Qiskit's QAOA and the minimum eigenoptimizer object to do optimization in Qiskit with only a few lines of code. So in Qiskit, the QAOA class is located in qiskit.algorithms, and it directly inherits from the variational quantum eigensolver class VQE. And so let's talk about a little bit about what arguments we can give the QAOA initializer and how they change the QAOA object. The first input parameter that the QAOA takes, and you can also see this down in the line down here, is an optimizer. So this argument refers to the classical optimizer that we're going to use to update these circuit parameters. Remember that in the QAOA, similar to a variational quantum eigensolver, we have this update loop where we start out with initial parameters and then we use a classical optimizer to iteratively adapt these parameters. And so this argument simply refers to the optimizer that we use here. Now, Qiskit itself provides a number of different optimizers. These are all objects of Qiskit's optimizer class, and you could also provide your own optimizer by creating an object of that class or subclassing this class. And so some of the basic optimizers that we are going to use in a bit ourselves are the Copula optimizer, the SLSQP optimizer, and then the Adam optimizer. The second argument that the QAOA takes is called reps, and this is basically the number of layers in the QAOA variational form, so the depth of our algorithm. Again, recall that for higher values of P, we can obtain better results, but the optimization becomes a lot harder as we introduce more parameters. The argument initial point refers to optional initial parameter values for beta and gamma to begin the optimization with. And so in a little bit, we will see that this initial point can make quite the difference on whether we find a global optimum or whether we get stuck in a local optimum. The argument quantum instance refers to the quantum instance that we run the algorithm on. So this can either be a simulator or a real hardware device, but today we're only going to work with these simulators. And then last but not least, we can also provide a callback function which can be used to monitor the optimization process. And in a little bit, you will also see what the format of this callback function is. Okay. One more thing we need is the minimum eigen optimizer object. And this is basically a wrapper for the whole optimization process. What this does, you can see here, it takes as input a minimum eigensolver. One possible minimum eigensolver is QAOA, but we could also plug in a different variational quantum algorithm. But in this case, we're going to work with QAOA. And then once we have initialized the eigenoptimizer, we can use the solve function of the object to solve a combinatorial optimization problem that is represented by a quadratic program. So let's go through these couple of lines here. Again, we first of all get our quantum backend that we want to run our quantum circuits on. We then initialize QAOA. As an optimizer, we use the Adam optimizer. The quantum instance is our simulator. We are going to use a QAOA of depth 1, and the initial point, we're just going to choose the 0 point. Then we initialize the minimum eigenoptimizer, and we just pass this QAOA object into the constructor for our minimum eigenoptimizer. And then after creating the quadratic program for our graph above, we can get an optimization result by calling the method eigenoptimizer.solve with the quadratic program. And so this is going to take a little bit, but you can see that once it finishes, it should produce the optimal result for the graph problem that we've defined above. Right. And so you can see that this result object, it has a number of different properties, but if we print it just like this, it already shows us the optimal function value that we obtained, then the solution, so the optimal bit string that it found, and the status of the optimization, so whether it was successful or whether it failed for some reason. The result object also has a property that gives us the final samples that were obtained from running the algorithm. We can obtain these samples by calling result.samples, and we can use the function that is defined here to plot these samples as a histogram. And so the code is not important for you to understand, but basically what it does, it just creates lists of the different probabilities, values, and bit strings, and then it will plot these as a bar diagram. We can see the result of this down here. So what this graph shows is basically the distribution of our final quantum state over the different computational basis states. So each of these bit strings corresponds to one computational basis states, and the final quantum state of our optimization process is in a superposition of all of these states. Now, the height of the different bars in this diagram shows us the probability of sampling this exact bit string when we sample from our quantum state. So basically, the amount of overlap that our quantum state has with the corresponding bit string or computational basis state. Additionally, we can see on the colors here what the function value, so the cut value for these different bit strings are. And so we see a result that we would kind of expect. We get a larger overlap with bit strings whose function value is very high, so who have a very good cut value. And we have a lower overlap with quantum states whose value is pretty low. But you can also see that it's not a perfect ordering. And in fact, we will see in a little bit that depending on where we start the optimization process or which optimizer we use, we don't always get such a nice result for the final quantum state. And this brings us to the next section, where we are able to explore the QAOA optimization process in a bit more detail. And so basically what we are going to do here is we are going to run the QAOA with different settings. So we can plug in different optimizers or different initial points, and then we are going to track the optimization process over time. So first of all, in the code below, what I've done is I've created a dictionary of optimizers that you can use to plug into the optimization procedure below. And so right now, this only includes the Cobila, SLSQP, and Atom optimizers that were also mentioned above. But you can plug in your own optimizer here. You can take a look at the Qiskit optimizers that are available and choose to explore different ones. Then what we're trying to do here is we're trying to run the optimization, but also record the different parameters that we encountered during the optimization, as well as the energy values. And we do so with this trajectory dictionary, which has entries for the beta values, the gamma values, and the energy value. And here we are going to define a callback function, which is going to be used during the optimization. So let me explain this callback function to you a little bit. When we pass this callback function to the QAOA initializer down here, basically what the algorithm does during the optimization process is it will periodically call this callback function with 4 arguments. The first one being the evaluation count, the second one being the parameters that it's currently evaluating, so in this case beta and gamma. The third one, the sampled mean, so this would be the energy value of the current state. And then the last one, the standard deviation for the different measured samples. Right, we only need the mean and the parameters, and our callback function simply consists of appending the parameters to the trajectory here. One thing to keep in mind is that in the Qiskit implementation, the parameters are ordered in a way such that the gamma parameter comes first. This is why we append parameter 0 here, and the beta parameter comes afterwards. And the reasoning behind this is that this is the order in which they appear in the quantum circuit. But yes, of course, alphabetically, it would be the other way around. So this is something to keep in mind when you are reading through this code. Okay, so then we again create our QAOA object with a optimizer, quantum instance, an initial point, and our callback function. We create our minimum eigenoptimizer, and then we run the optimization. So we have already seen this before. And then we can use this method QAOA widget to plot the energy landscape of the corresponding problem. This is still the MaxCut problem that we've defined above, together with the trajectory of our optimization. And so in total, it should look something like this. Let me just zoom out so we can see the full widget here. Okay, so maybe let's go from left to right in this widget. On the left, you can see the energy landscape of the problem. So you can see the X and Y axes, we have the gamma and beta parameters. It's a little finicky to turn this, but we should be able to see if we zoom out a bit. And then on the Z-axis, we have the corresponding energy value for the trial state of these parameters, beta and gamma. You can also see that on this optimization landscape, we've plotted the optimization process. So I've already run this optimization with the Atom optimizer and starting at a point which is located around here. And you can kind of see how the optimizer, maybe we zoom in a little bit, how the optimizer finds its way up this hill and actually to the global maximum, which is exactly the behavior we would like to see. Right, then to the right here, we plot the energy value of the different iterations. So for each of the parameter steps, we plot here how the corresponding energy value changes. And this is kind of just the height profile of the curve that we can see in the energy landscape to the left. And then to the very right, we plot the final samples or the samples of the final quantum state, again, as a histogram over the different computational basis states. And this is just as the plot that you've seen above. So again, this is kind of, we can see that this is a good solution because it has large overlap with states that have a very high value and small overlap with states that have a very low value. Okay, so this is how the optimization looks like. And now you can sort of explore this and play with this by plugging in different values. And so maybe let's start by plugging in a different optimizer. So instead of using the Atom optimizer, we are just going to use the Cobila optimizer here. Okay, if I run this code again, it should take this actually went pretty fast. It takes a little bit to do the optimization. But you can see that the Cobila optimizer looks much different from the Atom optimizer. And in fact, it fails to find the global optimum. So we can already see here an example of an optimizer that kind of gets stuck in a local maximum. So we again start at the same point of the optimization, but for some reason we end up at this local hill. Okay, so we can see this reflected in the energy value, which doesn't get much higher than 16.5, whereas before we went to an energy of something around 20. And we can also see it in this final sample graph. We see now that the colors are not ordered anymore. So we have large overlap with some quantum states that have a very bad value and only very small overlap with the ones that correspond to the optimal solutions, which we actually would want. And so this only shows that it's very important to appropriately choose the correct optimizer or to appropriately initialize the optimization procedure, because otherwise we're not able to find good optima within the energy landscape. Now, we also have to keep in mind that for us, it's not only important to get an overall good energy value, but we're only interested in one good solution. And so if we have if we end up in a local optimum that has a sufficiently large overlap with the actual optimal bit string, this might still be fine because we might still be able to sample this bit string at some point. And at the very end, we're only interested in the best bit string that we sample. This goes kind of into the direction of the CVAR adaptation that I've talked about in the previous lecture, where instead of looking at all of the bit strings that we sample, we only look at the best ones. By doing so, we can actually adapt the energy landscape. And what happens is that we will kind of widen the minima and maxima, which makes it easier for the optimizer to find these global optima. So as one last thing, let's try to actually adapt the Cobula optimizer in order to improve the optimization. So we can see that the reason why Cobula fails in this case is because at the very beginning, it kind of shoots off very far to the side, and then it gets stuck in this local maximum. And so the Cobula optimizer actually also takes some initial parameters, one of them being the initial step size. So this would be the initial change that it applies to the parameters in order to kind of gauge the energy landscape. And so by making it smaller, we might reduce this effect of Cobula shooting off to the distance somewhere and keep it more towards this close optimum, towards this global optimum. And let's also give it a little bit better starting value. Let's say 1.8 and 6.2. And then let's see what happens. Okay, so and just as expected, I mean, we helped out Cobula a lot by putting it basically almost on the global optimum itself, but by reducing the step size and changing the initial point, we were able to guide the optimizer sort of towards this global maximum. And so, of course, there are a number of different strategies. One of them being changing the energy landscape itself through algorithmic adaptations. Another one being using different random starts, so using different initial parameters and sort of taking the best optimization process out of a number of them. But yeah, in general, this is a highly non-trivial problem, and you can imagine this is the case for p equals 1, where we can still visualize the landscape, but things get even more complicated as we go towards higher values of p. Now, one more thing I want to point out in the energy landscape above is the periodicity in the different parameters. I briefly mentioned this in the previous lecture, but basically what we see in the energy landscape here is a periodicity in gamma and also in beta. For beta, this periodicity is always fixed to a value of pi, simply because the rotational x gates that are parameterized by the beta parameters have periodicity 2 pi. Now for gamma, this periodicity value can actually change. You can see, for example, that in this case, or for this energy landscape, we have a periodicity of 2 pi. This sort of makes sense because in the example that we've defined above, we only used integer weights. And if we take a look at the corresponding QAOA circuit, we can see that the rotational Z gates here are parameterized by gamma times some integer value. And so since the RZ gates also have periodicity 2 pi, we know that the same periodicity will appear in the gamma parameter. However, for the gamma parameter, the periodicity is much more dependent on the weights of the problem. So if we were to choose floating weights between 0 and 1, for example, we wouldn't have any periodicity at all in the gamma parameter. So this brings us to the last section of the notebook, where we will explore the effect of higher values of p. And so to recap real quick from the previous lecture, we saw that the global maximum or the global optimum of the QAOA energy landscape only improves as we increase the depth of the circuit. And this is because we are basically increasing the subspace of the Hilbert space that we are searching for in. We can also prove with the adiabatic theorem that in the infinite limit, we are guaranteed that the global optimum actually is the minimum or the maximum energy value. Now, in the to see sort of the effect of the depth value in a more empirical sense, what the code below here does is it will solve the quadratic program of the maxcut instance that we defined above for different values of p. And while doing so, we will record the energies, the runtimes, and the number of evaluations that we need in order to run the optimization. Right, so if we go through this code, we again define a callback that is just there to record the maximum number of evaluations. And here we basically time the solve method of the eigenoptimizer to see how the runtime changes as we increase the depth parameter p. And then the code below here is simply code that is related to plotting the different graphs. And so you can see I started this a little while ago, but the code is still running. So it might take some time for you to run this code as well. Okay, so once the code has run, it should look something like this. So we see 3 different graphs corresponding to the energy value, the runtime, and the number of evaluations for different depth values of P. And so the first thing we see that the energy value, while showing an upward trend, isn't necessarily the best for the highest depth. And the reason for this is probably that we do not find the global optimum in these optimization procedures here. And so there's really a trade-off here in choosing the right depth of the QAOA, because while we theoretically increase the value of the global optimum, it becomes harder and harder to find this global optimum. And so if we do in this little empirical study we did just here, we saw that the maximum value is actually obtained for a depth of p equal to 5. Now, the scaling for the runtime is a bit more straightforward. We can see that the runtime increases significantly as we go to higher values of p. And then for the number of evaluations, we can see that we pretty quickly cap out at 1,000 evaluations. And this is simply because the Cobila has a preset maximum number of iterations of 1,000. But you can change this by just passing a argument called maxiter to the initializer, and then you could rerun this analysis with a Cobila with more number of evaluations. Okay, but for now, this is it. So I hope you've learned a lot during this lab session, and I hope you are comfortable now with, first of all, creating your own variational forms in Qiskit and using QAOA to solve optimization problems. I've added a few additional resources at the end of this notebook, which includes some more tutorials on QAOA and VQEs, but also some information on other variational algorithms, such as variational classifiers or variational quantum linear solvers. And I'm sure that a lot of these concepts you will also see again throughout this summer school. So I hope you had fun, and I hope that you enjoy doing the exercises and exploring this Jupyter Notebook by yourself a little bit.